Okay, so in this chapter, in chapter 8, we are going to be working with quadratic functions. And so we have to understand all of the characteristics about them. What is going to happen? What should we expect? What kind of information can we gain from them? So in your reading, hopefully you read about a quadratic function when it's written in standard form. Anybody see in there what the standard form is for the quadratic function?
Y equals ax to the second plus bx plus c.
Okay, so let's fill in that blank there. We have y equals ax squared plus bx plus c. That is the standard form of a quadratic function. Remind me, what is the standard form for a linear function that we studied back in chapter 4?
Y equals b.
Y equals what?
A equals b plus mx.
Y equals mx plus b.
Okay, that is slope-intercept form, y equals mx plus b, but standard form goes y equals ax plus b. So in other words, we have an x term and a constant set equal to y, so it's a degree 1 polynomial. The function rule is ax plus b is a degree 1. In this one, our function rule, ax squared plus bx plus c, is a degree what? 2. Okay, what does it say a can't equal for this?
0.
0. Why can't it equal 0, do you suppose? Why
Doesn't
can't a equal 0?
That doesn't matter what the variable is.
So it doesn't matter what x is, that would wipe out the ax squared term, wouldn't it? 0 times x squared, no matter what x is. 0 times anything is 0. Well, now we would lose our quadratic, wouldn't we? Now it would become what?
Just a
Linear binomial.
A linear, yeah, now it would become linear. So we have to have an a value not equal to 0. Did it say anything about that b and c can't equal 0?
no.
No, okay. In fact, looking at your homework that you did for today, will you look at the quadratic functions on that, please? What's the a value in number 2?
0.
No. 1. Remember when there isn't a constant in front of the x squared term, that means it's a 1. A 1x squared. What's the b value?
0.
0. What's the c value?
-5.
-5. So it has an a value that is not 0, and it has a b value that's 0, but that's okay. It still produced a quadratic graph for us, didn't it? It still created a U-shaped graph. Okay. How about number 5? What's our a value? -1. -1. So are there any of those 5 that have an a value of 0? No, if they had an a value of 0, what would have happened?
It wouldn't have the lawyer had.
You wouldn't have that U-shaped smooth curve. You'd have a line. Instead, it would have been linear if a would have been equal to 0. Okay, so what's the basic one called? Does it say in there anything about that? What the basic one is called? Back a while ago, we learned that every function has a parent, a family that it belongs to. So we are going to say that the basic one is called the parent function. And remember back when we were studying linear, what was the parent function for linear? Anybody remember that one? Y equals something. So if standard form for a linear function is y equals ax plus b, what's the parent? What's the most basic parent function one that we learned for linear functions? Okay, but with a equal to 1. So y equals x. That was the parent function for the linear family. Y equals x. A is equal to 1, b is equal to 0. Well, for the quadratic family, the basic one would be y equals x squared. Same thing, a is equal to 1, b is equal to 0, but because there's a third term in quadratic, c is also equal to 0. So the basic parent function is y equals x squared, where a equals 1, b equals 0, c equals 0. Did you have to graph that one in your homework? No. You did not have to graph that one in your homework. You did not have the one where a is equal to 1, b is equal to 0, and c is equal to 0. So just like we learned with the parent function of the linear family, the parent function is the basic one, and all the other linear functions are transformations of it. So this is the parent basic one for the quadratic family, y equals x squared, and all 5 of those you graphed on your homework for today were transformations of the parent function, okay? So what do we call the graph? What do we call that smooth curve that it turned out U-shaped? Anybody know what it's called? It kind of looks like you would say parabola, but it's parabola is how we actually say it. Parabola. Kind of a cool word. Parabola. The U-shaped graph for a quadratic function is called a parabola. It either opens up or it opens down. Look on your homework again. Tell me, do you think there's anything that you can say why? Sometimes it opened up and other times it opened down. How many do we have that opened down? Oh, just the one? Okay, so the other 4 opened up. Okay, find something they all have in common then, those 4 that all opened up, and how they are different from that one that opened down.
The one that opened down, the first and last numbers were negative and the rest were positive. And when it opened up, the first and last numbers were positive. The middle ones were negative.
What numbers are you talking about?
Like on the chart.
On the chart, in the table, the input values.
Yes, where x is equal to -5.
The input values or the output?
Like X or Y.
The Y.
The y, the outputs?
Yeah.
Okay, you think that's the reason? How many points does any graph actually have? That is a continuous graph. These are continuous, infinite. So this is just a small picture of the inputs and the outputs. So it really doesn't have anything to do with the inputs and the outputs. It has to do with something else in those equations. See if you can figure out what it is. What is it that's
The A value was negative.
The negative 1.
all of when the a value is negative? What did the parabola do?
Go up, open down.
It opened down. When and so in all those other ones where it's opening up, are the a values all positive?
Yeah.
Yeah. So it's the a value that controls whether it opens up or it opens down. It's a role that a value plays, one of its roles. So when a is greater than 0, when it's positive, what's going to open? Up. When a is less than 0, what's it going to do? Open down. So again, that should be kind of like a little way to check, just like we did with linear functions. We said, if it has a positive slope, it better be doing what? The line better be increasing, rising from left to right. If it has a negative slope, it better be dropping, decreasing from left to right. So same thing with quadratics. When you're done graphing them, if you don't have this nice smooth U-shaped graph and it's not opening the correct direction, then you should be able to identify that pretty easy. Say, hey, wait a minute, why is my parabola opening down when my a value is 3? That would be a problem, okay? Anybody know where all of these changed direction at a certain point, didn't they? 2, 3, 4, 5, and 6. Did they all change direction at a certain point?
Yeah.
Okay. Anybody know what that point is called? I have to go further into the lesson to find it, yes. What's it called, AJ? A vertex. It is called a vertex. The vertex plays a big role in a quadratic function. It is where the parabola changes direction. In fact, it is the only point that does not have a point symmetric to it. When you look on your graphs from that homework for today, does every point except that turning point, that vertex, have another point across from it with the same y value.
Yeah.
Yeah. That's called a symmetry point. There's symmetry going on there. Can you find the vertex in the table?
Yeah.
That's true where the vertex is in the table. Look on your homework.
It's when
It's
it like.
usually either the highest or the lowest.
It's either the smallest y value or the biggest y value. And it's the only one that doesn't have a repeat y value, isn't it?
Yeah.
Yeah. It's the only one that doesn't have a repeat y value. So they chose input values that would guarantee that you would get the vertex, and it would kind of be right there in the middle of your table. So if there are 5 ordered pairs, I don't think in any of them that small. Number 2, there were 7 inputs. What's the vertex in that one?
Negative.
Which one is it?
0, 0.
0, -5. It's kind of right smack dab there in the middle, isn't it, of the table, only because whoever put these input values together said, you know what, I want them to be able to see the nice U-shaped graph and its symmetry. What's the vertex in number 3?
-2, -4.
-2, -4. Notice something about the y values on the other side of that -4. What's true?
The same.
They're the same. And then if you go up one more and down one more, what's true about the y values?
It's the same.
They're the same. Oh, can you see the symmetry in the table too? Right? Okay, so when the parabola opens up, so we have this turning point, and when the parabola is opening up, the y value of that vertex, because the vertex would be the lowest point on that curve, wouldn't it? And low and high mean the y-axis, the vertical axis. So when the parabola opens up, the y value of the vertex is called a minimum. And I want you to circle the y value so that you remember that it's the y value. When they are asking you for the minimum, they want you to give the y value of the vertex. What's the lowest y value, in other words, on that curve? When the parabola opens down, now the vertex is at the top, isn't it? So when the parabola opens down, the y top value of the vertex is called a maximum. It doesn't go any higher than that. And again, let's circle the y value, not the x value. X value doesn't talk about height. The y value talks about height, up and down. So you're going to have to make sure you have a good understanding of minimum and maximums. And then one more thing here, it says a parabola has an imaginary line that divides the parabola into 2 symmetric halves called, anybody know what it's called? This dashed line that I've drawn through those 2 parabolas there? Anybody know what that's called? Another characteristic of a parabola of a quadratic function. Anybody find it yet? I might have to give it away. Okay. Axis of symmetry. They might not give that away yet in this lesson. We are going to be working also with an axis of symmetry. So the axis of symmetry is this right here. This dashed line drawn right through the vertex of the parabola. The axis of symmetry divides that parabola nicely in half. Everything on the curve on one side of that imaginary line has a point symmetric to it on the other side, same distance away on the other half. Okay, so these are all kind of important things that you need to make sure you understand at this point about a quadratic function and its graph. So questions? Okay, then let's go to the back side and let's start talking about how can we identify quadratic functions if we don't have a graph? What if we don't want to graph them? So to identify if a function is quadratic when given in equation form, first thing you need to do is get the y alone. It needs to be set equal to y, just like we talked about slope-intercept form for linear functions. We want it set equal to y. we basically then want it written in standard form. So we're gonna get the other side put in standard form. Well, what is standard form again for the?
Y equals ax squared plus b plus c.
Yeah. So we gotta make sure then, does it look like it is of this type of form? Does it have, at the very minimum, it has to have a what? An ax squared. It has to have an ax squared, doesn't it? At the very minimum. Okay, so we don't want to have to graph, so instead we're going to follow these instructions. It says get y alone. Okay, so let's look at number 1. What do we have to do?
Subtract 6x.
Get the 6x out of there. Move it over to the other side. Y wants to be alone. So we have negative 14 minus 6x. Well, let's put that in standard form because that's what we're supposed to do next. No? What would come first?
Negative 6.
Negative 6x followed by
Minus 14.
minus 14. Is that quadratic?
No.
No.
No, it's not. What is it? In fact, this would be linear. So in other words, it is not quadratic. And our reasoning would be a equals 0. If there's not an x squared term, that means our a is 0. And remember, we can't have an a value of 0. Can we have a b value of 0?
Yes.
Can we have a c value of 0?
Yes.
Yes. Okay. Okay, number 2. 2x squared plus y equals 3x minus 1. And you do not say it until you get it in standard form. Or in other words, get the y alone. So what are we going to do to get the y alone in this one?
Subtract 2x.
Okay, we'll subtract the 2x squared. Okay. So now the y is a 1y alone. We have 3x, take away 1, take away 2x squared. None of them are like terms, are they? Don't really have anything to subtract that 2x squared from except 3x minus 1. So now we'll put it in standard form. What would be first?
Negative 2x.
Negative 2x squared, followed by,
3x.
what am I going to do with that 3x? Add it, because it's a positive. And then followed by, subtract 1. Is this quadratic? Okay. Is quadratic? What does a equal?
Negative 2.
A equals negative 2. Well, if a is equal to negative 2, you guys should be able to tell me something about the graph of this.
It's going to open down.
It's going to open down. Why?
Because the a is negative.
Because the a is negative. So without even graphing this, we should expect that we would see a parabola opening down. That much we know right now, don't we? Okay? Because it's quadratic, so that means it has to be a parabola. It has an a value that is less than 0, so that means it has to be opening down. So this is the kind of stuff we would do for determining if an equation shows a quadratic function or not. So questions about that? But you're not doing any graphing in your homework, you're doing more of the kind of identifying. Okay, well then let's go look at, before we do this next one, I want you to go look at, back at that page 522. Does anybody remember from a table of values, inputs and outputs, how did we determine if a function was linear or not?
If x and y change at the same rate.
Okay, do they have to both change at the same rate, or do they both have to have a constant
One
change?
is a constant change.
They have to have a constant change. So let's look at number 1 in your homework. What's happening in that one? Find a part of the table where maybe you can tell. Can you tell? Or maybe you might have to look at your graph. What's happening? Number 1 on your homework. That was linear. What's going on? The x's aren't changing at a constant rate, are they?
No.
That makes it kind of hard. Okay, well let's slip in then. It would be helpful if we had just had x equals 1. When x is equal to 1, can you tell what the y value should be? What would the y value be for x equals 1? Negative
1.
1. Okay, so if that would be negative 1, we would slip that in. Would you just slip it into your table between 0 And negative number, not on there, you're not going to, because there you go, yours there. So in the table, will you slip in between 0 and input value 0 and 2, will you slip in 1? And then for the y value, it would be -1. Okay, now, as the x's are increasing by 1s, starting at the bottom of the table, what's happening to the y's? What are they increasing by?
2.
Are they going up 2? From -5 to -3, what's that? +2, isn't it? From -3 to -1, that one we just stuck in there, is that a +2? Yeah, okay. From -1 to +1, is that a +2? Yeah, so there's a constant change in y's in what we call the first difference. Okay, let's go look at number 2, which is quadratic. Number 2, which is quadratic. Well, that one's very nice. All the x's are going by 1s, aren't they? Okay, what's happening to the y's? Are they changing at a constant rate?
We're going down by 3, and when it hits the vertex, then it goes up by 3.
Well, does it always go down by 3?
No.
Even to get to the vertex, does it go down by 3? It doesn't, does it? And then all of a sudden, besides that, then it switches from going down to going up, doesn't it? So that means a quadratic function can't have a first difference that is constant. And what does it show in the book it should have?
Second.
A second difference that is constant. So, in other words, after we figure out the first difference, then we figure out from that first difference what would the second difference be, and that's where the constant should show up. Okay, so let's do one on here. Let's see if this one is. Would this give us a quadratic function if we graphed it? To identify if a table of values or a set of ordered pairs represents a quadratic function, look for a constant, or sometimes they just call it a common second difference in y. When there is a constant change in x. So you can't be checking any place where there isn't a constant change in x. You got to make sure you're only checking where the x's are changing by a constant change. Then you check to see do you have a constant second difference in the y. So in this one, x has a constant change of what? What's it doing? It's going up 1, isn't it? So it's increasing by 1. Okay, let's find the first difference in the y. So let's decide if this is quadratic or maybe it's linear. How will we know if it's linear? Will it have a constant first difference? Yeah, remember that's where if a first difference shows up in it, then that makes it linear. Okay, what's going on from 39 to 18? Subtract 21. It's going down to -20. It's going 21 units down. How about 18 to 3? Subtract 15. It's already not linear, right? Why?
It's not a constant.
Yeah, they're not the same. 3 to -6. Going down 9. -6 to -9.
Plus or minus 3.
It's still going down, isn't it?
Yes.
Okay.
It's -6. The second difference is -6.
Okay, and so now that's not a common first difference, a constant first difference, so then we go with this one, and now we only have 3 of them to find, because we go from -21 to -15. Is that a +6 or a -6?
Minus.
Really?
Plus
From
six.
this,
Going up, it's less.
it's going up, isn't it? It's getting,
Zero.
yeah, it's getting closer to 0 now. From -15 to -9,
6.
+6. From -9 to -3.
6.
Yeah. So we would say that it is quadratic. We would expect this to show us a graph that is a smooth U-shaped curve. And we would say because second difference is a constant 6. It's a positive 6. So there's our reasoning. You gotta write that out. You gotta show what's happening. Otherwise, you're gonna have to graph them. Well, tell me me something about why you think this happens. The constant change shows up in the first difference in a linear function. The constant difference in y shows up in the second difference in a quadratic function. Let me let you in on a little, like, pre-sneak of cubic functions. The constant difference for a cubic function shows up in the third difference. Why do you think that is?
Because when it curves, they're the same y values across each other.
So we have that symmetry going on. Tell me something about a linear function again that has a constant first difference. What's its degree? 1. Tell me something again about a quadratic function that has a constant second degree. What's its degree? 2. Tell me something about a cubic function. If it has I've already said to you, it has a constant third difference. What degree is the cubic function? 3. So we know we have what type of function we have based on the constant difference in the y values. If there is no constant difference that shows up, then we probably don't have a function. What's a function again? Oh, that was back in chapter 3. What's a function? Okay, let me get you started. Each x value has
Has one
only
y value.
one y value. Each x value has only one y value. So in other words, what's the vertical line test again?
If there's
You draw a line.
Any vertical line you draw through the graph can only cross through one point, right? Because each x value can only have one y value. Okay, this is just our start on quadratic functions. Any questions?
No.
Okay, let's go ahead and get you started then. Pass your homework up.